Okay, so the first talk is going to be about what we call contract-based integration of CPS analysis. Basically, let me start with the motivation. We know what we call CPS or cyber-physical systems are systems that interact with the physical world, right? So it's software-aligned systems that interface with the physical world. It means that whatever verification of behavior we do needs to take into account this physical world, and they need to work in synchrony. The typical kind of problems or systems we will see that has problems will be, for instance, the airbag. We know a lot of news about the airbags. Typically, if they don't inflate on time, obviously you will hit the steering wheel, and that will, of course, will not work. So that's kind of the style. But obviously, that's a very simple system. We have more complex systems. And these more complex systems are, of course, airplanes, big airplanes, are the full cars, but are also systems like the smart grid. So the smart grid is actually very complex. It's managed by software and operators. And as we make progress on this, smart grid, then we need to take into account a lot of different agents that kind of managed by software that will interact through physical phenomena, in this case, for instance, the electricity. Right? Now, these systems actually need, or today are developed with a lot of analysis. So we do analysis on them. We use analysis tools. We have been hearing about these model checking tools that we use, that, for instance, Microsoft has really relied on to get good drivers. But also, if we go for an airplane, so we need to do analysis of the aerodynamics. We need to do analysis of the power management. We need to do analysis of the timing, right? So all of these multiple analyses are developed actually from different, I would say, scientific domains. They develop by themselves, and then when we put them together, that can create problems that can be problematic. And that's what we focus on here. Just to give you a very brief idea of the kind of problems we face in, I will call it multi-tier industries, like the avionics industry. This is kind of an idea of what happens with the Boeing 787, the different suppliers, right? These different suppliers are coming from all over the world, multiple organizations, and all of them kind of develop different pieces. So whenever they put them together, then we start having problems. Probably one of the most famous problems you have heard about is the battery thermal problems, batteries that just burst into flames. And that's actually something, well, very bad to happen, of course. And this is not only the case for the Boeing 787, it's also Tesla had these kind of problems. Perhaps they have better PR, so they manage that much better, but the problems are still there, right? So what are we talking about when we talk about these analysis contracts? I mentioned that these different tools, different analytic techniques, are developed in different domains. So it means we will have experts, for instance, that will focus on real-time scheduling. I work on real-time scheduling, so I will be one of them. We will play with frequency scaling, reduce the power consumption. But then you will have also other experts that work on battery scheduling. Kind of the new technology on battery is that you connect and disconnect battery cells, so you can have discharging and charging cells at the same time. Think about a hybrid car, right? And the benefit of having this connection between cells is that you can reach the appropriate voltage by connection, right? So you connect them instead of doing an analog adjustment of the voltage, which is more efficient. Which is very good, but the problem is the next one, right? It means that, of course, we have these batteries that overheat. If we change the connections between the cells, then we have different properties of thermal dissipation. And if we have different thermal dissipation, then we can run into problems such the things that happen with Tesla and the Boeing 787, right? Notice that when I'm talking about these different analyses, meaning that there are different people working on them, and they do not talk to each other, right? If they don't talk to each other, these interactions that I have been discussing will not be discovered until you put them together, you try to fly the airplane, and suddenly there are flames in the airplane, right? So we need to find out why. So what we go after is to say, well, we have a model of the system, right? In this case, we are using as our modeling device, AADL. Actually, AADL allows us to do an analysis of the system that allows you to add multiple analyses, exactly what we have been saying, right? So for instance, it will allow us to do scheduling, real-time scheduling. It will allow us to do frequency scaling, control stability analysis, if we put the proper, let's see, annotations to do that kind of exploration in MATLAB or things like that. But whenever we put them together, of course, one of the things we are going after is having these contracts. So it means we describe the interactions between these different analyses. Notice that we are talking about the analysis and not the model. And the reason for that is that modeling is part of the semantics, but it's not everything. In the end, the analysis is the one interpreting the model that has the final semantics. And that's one of the things we wanted to kind of capture, right? So how do we do this? Basically, as I'm putting here in the slide, we kind of capture assumptions and guarantees. What are the assumptions that analysis make about the system? And what are the guarantees that I provide after I run my analysis successfully, right? I put them together and find out what are the interactions that I have between them. To be able to do that, then what we need to do is, first of all, define a language. We call it a domain, where I can express that interaction between contracts, right? And once I have that domain, then I will put actually the contract that actually talks about multiple analyses together, the multiple analyses that will interact. Now, I will not ask you to understand this. Just take the shape of what it is. But when we talk about that domain, which I will need to lean over, we need to describe, first of all, what we call the objects that we talk about, threads, battery cells, connections. All of that is the language that we describe in our domain, right? All the objects. Then we express static properties that we express in our AADL model. These are all these static properties. This thread runs at 10 hertz. That's one static property. We describe runtime properties that are the ones that we need to observe. What are the interconnections? How the interconnections will change. And with all that, then we can describe formulas that we can verify. And then those formulas are using the contract where we express the input, the output, and the assumptions and guarantees that are actually these formulas that are verified with some verification engines that we have. Right? In particular, we use SMT for first order logic, the static properties, and LTL, linear temporal logic, to verify the runtime properties. So as a very brief example, just to give you the shape of this, imagine a surveillance aircraft, and we have all these different analyses: security, schedulability, frequency scaling, logic, not deadlocks or the rest conditions, battery scheduling, and battery thermal analysis. When we put them together, obviously, again, don't look into the details. This is the style of the formalization that we get out of it, right? Of course, there is no intention for you to understand that, but we can get to these details, right? Exactly what are the conditions that we need to test about the intersection of all these different analyses, right? So once we have that, then we can use our we can reason about how they behave. We can prove, for instance, that for the assumptions of frequency scaling, we can assume that under certain conditions, deadline monotonic scheduling is similar or is the same, will behave the same as rate monotonic, or EDF will behave the same as rate monotonic if we have certain synchronicity, certain harmonicity, and the like, right? So all of this is possible to do because we have an engine behind that is able to understand that and verify this automatically. Obviously, I will not talk too much about this. It's another assumption for the battery scheduling about the neighbors and the thermal characteristics of the neighbors. We need to make sure that this will work. Again, once we have these contracts, the contracts will express the dependencies between the different analyses, right? This is a dependency graph. And in that dependency, we know what part of the model we are using, what part of the model we are modifying, and finally, what are the conditions that we need to test, which is of them. Implementation, very briefly, we make this in Osare. We have two tools to verify the conditions. And we created a sublanguage to express these contracts.